Hello everyone, I'm Jinjin Xu from ByteDance AI Lab. Today I'm going to share my recent studies about green learning. Before we start the main topic, I will show you what is green learning and why we need green learning. With the development of deep learning, many neural networks have achieved solid performance on many tasks like machine translation and image classification. However, despite good performance, the computations required for these neural networks have increased dramatically. According to an OpenAI blog, the computations required for the largest AI training runs has been surged by 300,000 times since 2012 to 2019. And these computations also bring a surprisingly large carbon footprint. According to an article from MIT Technical Review, training a single AI model can emit as much carbon as 5 cars in their lifetimes. So if we carefully analyze these deep neural networks, we will find that most computations come from two parts, that is network architecture and data. First, network architecture affects downstream performance. However, network design and network search are expensive things since they require thousands of full training on downstream tasks. First of all, the size of a network architecture is becoming bigger and bigger. Second, large-scale data covering multitasks and multi-languages also bring a lot of computations. First of all, for natural language processing tasks, the granularity of token segmentation decided by a vocabulary also affects downstream performance. However, vocabulary search is also an expensive thing because it also requires a lot of full training on downstream tasks. So the target of green deep learning is to explore an environment-friendly learning solution. It focuses more on the energy efficiency of AI systems. And in this presentation, we focus on a more challenging problem. Can we achieve good results without training? And we propose to training-free solutions, including one training-free network architecture search solution and one training-free vocabulary search solution. The first one is about training-free network architecture search. I will first present network architecture search background and describe our solution, followed by some experiment results. Okay, here is the main questions will be described in background section. They are: what is network architecture search, short for NAS? What is the current research progress for NAS? What are the open challenges in NAS? And what are our contributions to NAS? As we all know, in the past 10 years, the success of deep neural networks relies on their designs. Researchers developed more and more advanced networks, and these networks constantly break through the bottleneck of performance on a lot of AI tasks like image classification and machine translation. However, it takes lots of human efforts to design a well-performing network. And now, in fact, many researchers and engineers are often stuck in network design. We design a network to evaluate its performance. We run it on a lot of downstream tasks. And if the performance is not good, we fall back to the first step and design a new network again. So the fundamental question behind the NORS is, what is the best network architecture for the target problem? Formally, a network architecture search is a task to automatically search well-performing network architectures. Here is a brief summary of recent NARS studies. The search process of NARS can be split into 3 components, including search space, search method, and evaluation method. Search space defines all candidate networks that can be examined to find the final architecture, and search method defines a solution to explore search space. Evaluation method is responsible for helping a search method to evaluate the performance of architectures. Currently, the existing widely used search methods can be split into 5 categories, including random search, evaluationary search, Bayesian search, differentiable search, and IO-based search. Here is a quick view of the computations required for different NARS solutions. Initially, the NARS solution takes thousands of GPU days, and to now, our solution only takes 0.08 GPU days. This is a good signal to show that our solution is really a green solution. Okay, because most of computations in previous studies are used for architecture evaluation. So in this work, we aim to figure out a question, can we evaluate architectures without training? So to achieve this goal, it is essential to figure out how an architecture affects optimization. Let's take MLP network as an example. It contains L layers. Each layer contains a linear operation and a non-linear operation. Here is the gradient of weight in a layer. As you can see, the gradient is decided by multiple factors, including the activation function, the output of previous layer, the weight in linear operation. That is to say, gradient stores all structure information. And intuitively, gradient values affect the step size in optimization. Worse architectures are likely to bring the vanishing and exploding problem. So we argue that gradients are the most direct signal to evaluate the convergence and the generalization ability of architectures. Motivated by our understanding, we propose a hypothesis. It is there exists a gradient feature, short for gradient kernel, that can be used as a coarse-grained proxy for training to evaluate architectures. To support this hypothesis, we conduct a theoretical analysis and found a K gradient feature. It is the grand matrix of gradients. Each element in this matrix is a dot product between any two gradients from two examples or two mini batches. As we can see, the grammatics of gradients affect the convergence rate. And to be specific, the F norm of the grammatics decides the upper bound of convergence rate. Higher F norm is expected for higher convergence rate, and each element in this gram matrix is a dot product between any two gradient vectors decided by gradient value and the gradient correlation. That is to say, vanishing gradients and taxic gradients both get a lower dot products and lower F norm scores. That is to say, the grammatic can be regarded as a health index of gradients. Based on this theoretical results, we propose to leverage the grammatic of gradients to evaluate randomly initialized architectures. In implementation, the mean of the gradient metric of gradients is adopted. We call it a gradient kernel. And we conduct experiments on downstream tasks and calculate the Spearman score between a gradient kernel and K optimization metric, including training loss and validation accuracy. Experiment results demonstrate that the gradient kernel is positively correlated to optimization metric, including training loss and validation accuracy. The Spearman score is around 0.55 and the p-value is less than 0.01. So it is a good signal to show that the gradient kernel can be used as a coarse-grained architecture evaluation metric to evaluate architectures. So this also supports our hypothesis. According to this gradient kernel, we then propose a new NAS approach. First, we choose top K architectures with the highest gradient kernels at initialization, and then we evaluate them for training. The advantage of this solution lies in that in the first step, it does not rely on any training, so it is an efficient network architecture search solution. We evaluate our solution on this site, NARS Bench 201. It is a unified NARS benchmark, which provides plenty of network candidates. And here are our results on ImageNet 16. The last column shows our results, and the blue bar represents accuracy, the red bar represents speed up. As you can see, our solution achieves large speed up and keep good accuracy. We also apply our solution on various designs and models, including designs like translation, classification, and covering models like CNN, Transformer, and Robota. As we can see, our solution also can explore a better architecture than widely used architectures on various designs. So to conclude, in this work, we propose a new NAS understanding from the perspective of optimization and a fast and strong NAS method. The next work is about grain vocabulary search. As we all know, the choice of token vocabulary affects natural language processing tasks. So in this work, we aim to figure out what is a good vocabulary And whether can we find the optimal vocabulary without training? Due to the discreteness of text, vocabulary construction is a necessary step in natural language processing tasks. And now, most widely used approaches for building vocabularies are based on probability and frequency. Many previous studies have shown that the vocabulary size affects downstream performance. However, very few studies tune this hyperparameter since downstream training takes a lot of computations. Instead, most studies only adopt the widely used setting. For example, 3,000 to 4,000 is the most popular size in 42 papers accepted by WMT conference. So in this work, we aim to explore a lightweight vocabulary solution without training. To achieve this goal, it is essential to find a good vocabulary measurement as proxy of downstream training. We first give an understanding about what is a good vocabulary from the perspective of information theory. With the increase of vocabulary size, the average semantics or entropy represented in each token is decreased. If we do not consider costs, more tokens are expected since less entropy benefits for training. However, too much tokens also bring parameter explosion and takes token sparsity problem. So we suppose that a good vocabulary should have the maximum marginal utility with more benefits from an increase of cost and we quantitatively formulate the maximum marginal utility with the negative derivative of entropy to vocabulary size, short for MMU, and our experiment results show that MMU and the downstream performance are correlated on 2/3 of translation tasks. So based on this, our experiment results, we formulate vocabulary search as a problem that found the vocabulary with the highest MMU. Implementation, we leverage a smaller vocabulary to estimate MMU based on the difference of their entropy values. Since MMU is a dynamic feature depending on a contrastive difference, we also formulate this contrastive process to given an incremental integer sequence S with each time step representing a set of vocabularies with ST tokens. The objective function can be formulated as this function. And for simplification, we propose to optimize its lower bound. Given its lower bound, the whole search process can be split into 2 steps. The first step is to search for the optimal vocabulary with the highest entropy at each time step. And the second step is enumerating all timestamps and outputting the vocabulary with the highest MMU. However, due to the expositional search space in step 1, we propose to formulate the problem that found the optimal vocabulary with the highest entropy as an optimal transport problem. To be specific, we can imagine vocabulary as a transport process that transports charts into tokens. The number of charts is fixed, and not all tokens can get enough valid charts. That is to say, each transport matrix can build a vocabulary by collecting all token candidates with valid charts. Here, valid means that the transport matrix is required to satisfy several constraints, like chart A cannot be transported into token BC. Different transport solutions bring different costs. The target of optimal transport is to find the transport solution with the lowest costs. That is negative entropy in our solution. So here is the details of our vocabulary search solution. And we conduct experiments on multilingual MT and bilingual MT to evaluate the performance of our solution. We first compare our solution with widely used vocabularies. And as we can see, vocabularies searched by our approach are better than widely used BPE vocabularies with higher blue scores and much smaller size. We also compare our search solution with the naive search solution. The naive BPE search solution requires full training on downstream tasks, so it takes a lot of GPU hours, and our solution does not require any training, and it only takes 0.5 CPU hours. It largely reduces the search costs. So these results demonstrate that our solution is really a green solution. We also conduct experiments on various structures, and as we can see, the vocabulary searched by our solution shown in the bottom line in each group are better than the widely used vocabularies. In each group, the top line represents widely used vocabularies performance, and the bottom line represents our solution's results. And we observe the same and better results than widely used vocabularies on various structures like transformer big, transformer, and convolutional seek-to-seek. To conclude, in this work, we propose a new understanding about vocabulary from the perspective of information theory, and we propose a new green vocabulary search method. So that's all. Thank you.